Welcome back to the fourth video in the sixth lecture on Covidenomics, and in this video we're going to be looking at the mathematical appendix, not that sort of appendix, for the model that we presented in the previous videos. In the second video of this sixth lecture, when we were first developing this economic epidemiological model, we explained where this horizontal line came from. It comes straight out of the SIR modelling, and it gives the situation where the change in the proportion of the infected people in the population is zero. So there's a constant rate of infections each period. In this video, we're going to go behind the maths of the social activity choice curve that we have here, this downward sloping curve. Whilst its intuition is fairly clear, it's worthwhile running briefly through the mathematics because it will highlight some of the assumptions that we've got to get this curve. The decision facing an individual is going to have parts that depend on the benefits they get from social activity today, but also the future costs and benefits due to the risk of catching COVID-19. So let's look at the current benefits first. They're captured here by a standard utility function. So A is our level of social activity chosen by an individual. U is a utility function, or it represents the benefits that the individual gets from social activity. And we're going to make our standard economic assumptions that U is an increasing concave function, or in other words, it's increasing in social activity. You always prefer more social activity to less social activity. However, you have diminishing marginal utility from extra social activity. So whilst utility increases with more social activity, it does so at a decreasing rate. The future is going to be captured by these capital V terms here for the individual. So capital V is just going to be the continuation value, or the value in present value terms, of all the future utility that the individual expects to have in the future, starting in period t+1 in both cases. And the I just means that the individual's infected, and the NI is just that they're not infected. And we're going to assume that the value of not being infected is strictly greater than the value of being infected. In other words, if you're thinking about your life from tomorrow onwards, you would prefer to start tomorrow not having COVID-19 than having COVID-19. And that's a pretty reasonable assumption. We're also going to assume that these future values starting tomorrow do not depend on the proportion of a population that are infected today. Now remember, we're not saying that the likelihood doesn't depend on this proportion. We'll come to that in a second. What we're saying is that when you're saying today, what does the rest of my life look like if I wake up tomorrow with COVID-19, then that doesn't depend on the number of people infected in society today, all those other people that might have COVID-19 today. And similarly, when you say, well, what's the rest of my life look like if I wake up tomorrow and I'm not infected, that also doesn't depend on the number of infected people today. Now, we can imagine situations where this doesn't hold. For example, let's suppose that a higher number of infected people today means that there's stress on our hospital system. So that may mean that we get a lower value tomorrow if we get infected, because we may not be able to get a hospital bed, or we may not be able to get as good medical treatment. In that situation, VI will fall as IT on N rises. So it is possible to come up with these situations. We're going to make the assumption, though, that neither of these values starting tomorrow depends on the proportion of the population infected today. It doesn't depend directly. The probability of each of them, though, will. So we've got our probability here, P, which is the probability that we get infected today and start down this infected path tomorrow. So P is the probability that we wake up tomorrow and find that we've actually got COVID-19. It does depend on IT on N. The more infected people out there, then for any level of social activity, the more likely we are to get infected. So we expect this probability of future infection to be increasing in IT on N. We also expect this probability of being infected to increase in our level of social activity. So the more social activity we take today, the higher the probability that we will be infected tomorrow. So the probability of infections increasing in both our social activity level and in the proportion of the population who are infected. And obviously, if P is our probability of being infected when we wake up tomorrow, 1 minus P is our probability that we will not be infected when we wake up tomorrow. So we can write the individual's decision-making problem over their level of social activity by this simple equation here. Their current value, or their current benefit, their current utility today in time t, when they're not infected, is going to be equal to the benefits that they get from activity today, from social activity, plus 1 minus P, which is the probability that they're not infected tomorrow, times the benefit that they get of not being infected tomorrow, plus the probability that they are infected tomorrow, P, times the value that they get from if they're infected tomorrow, remembering that VI is less than VNI. And the probability depends on both the social activity and the proportion of the population who are infected today. Now, the individual is going to take this proportion as given. They're going to be small relative to the population, so they will just take the number of infected people as a proportion of the population as given, and they will be choosing their level of social activity AT today. So an individual will set their level of social activity today to maximise their discounted present value of utility, which is just the equation we have here. So here we've got our first order condition for that optimisation problem. It looks like it's going to be pretty well behaved. We've got our first derivative of utility with regards to social activity increasing. It's positive but at a decreasing rate. And over here, well, you prefer not to be infected than to be infected tomorrow, so that's a positive number there. And we know that the probability of being infected tomorrow increases in your social activity, so the PDA is going to be a positive number, negative sign there, so it looks like it's pretty well behaved. I'll let you check for second order conditions for yourself. We're going to come back to them actually in the next slide. What we're actually after here, though, is to look at how AT, our activity level today, depends on I divided by N. So that's the relationship we want. Now, some of you may not have seen this trick before, but again, it's just a bit of calculus. It's to note that this first order condition holds for each possible value of IT on N. So in other words, we can think of this as an identity here when we start thinking of it varying in terms of I on N. So we can take the total derivative, and if we do, we get this equation down here. Notice that the first bracketed term here, that's just the second order conditions from our optimization. So if we're actually looking at an optimal or a maximum with regards to our activity choice, this is going to be negative. What about this term over here? Well, clearly VNI minus VI, that's positive. We prefer to be not infected tomorrow than to be infected. This other term, this cross-derivative term, well, that's more problematic. It's not quite clear what sign that's going to be. But if we say take the simple example that I've mentioned before, the probability of becoming infected is simply your social interaction level times the fraction of a population who's infected. This second derivative is just going to be equal to 1, and so this bracketed term would be positive, this bracketed term is negative. We can then reorganise this equation, and that's what I've done here. So we've got the rate of change of activity level in time t with regards to the proportion of the population who are infected in times t. That's just equal to this division here. Remember, bottom part was going to be negative. In our example at least, the top part is positive. As long as that top bracket is positive, then this whole thing is going to be negative, or in other words, our activity level will be falling in the proportion of the population who's infected. And that's just exactly what we needed to get this downward sloping social activity choice curve. As the level of I on n rises, the level of social activity is going to tend to fall. Okay, so I hope you found that useful. Talk to you next time.